Chapter 5 is about solution concentration. There are some important vocabulary words in this unit, and there is a little bit of math. Not difficult math, though. So let's talk about the word concentration. It's a relative term. It means the amount of solute per the amount of solution. Your solute is the thing that you're trying to dissolve, and the solution, often known as the solvent, is the thing that you're dissolving it in. So for example, if I were making a glass of iced tea, I would use iced tea powder. That would be the solute, and my water, what I am dissolving it in, is the solvent, or which results in a complete solution. So here the example is 1 tablespoon of sugar dissolved in 1 cup of water has the same concentration as 2 tablespoons of sugar dissolved in 2 cups of water, because they have the same ratio of sugar to water. My sugar is my solute, my water is my solvent, resulting in a solution. Now, the reason why it says amount of solute over amount of solution is because the solute is the one thing, the solution is the two of them combined. So we calculate this in percent. So here we have weight per volume. So this is WV percent. So I want to show you what that would look like first. So it's going to be part over whole times 100. So all of these, whether I'm doing weight, volume, or weight, they're all going to be the same thing. It's my part over my whole. So if you look here at the bottom, it says a 5% weight volume solution contains 5 grams of solute in 100 milliliters of solution. So here's an example of a 50% weight volume glucose solution, though I do see a typo in this PowerPoint because it says weight volume, so this should be grams, because that would be weight. So 5 grams of glucose, and it was dissolved in 100 milliliters of solution. So you divide those two and then multiply by 100. So in this sample problem, it's asking what is the volume percent of a solution that contains 75 mils of glycerin with a total volume of the solution of 325 mils. So 75 over 325 times 100. Notice that the total volume of the solution is 325. That's including the 75 mils of glycerin. Now, we're solving for this problem straightforward, meaning if the equation were y equals mx plus b, right now you're solving for y, but sometimes you need to be able to solve for something else. So sometimes you might need to know how much solute is in a particular amount of solution. So that means you're solving for the numerator. So in this case, a 50% weight volume sodium chloride solution can be written as either 5 grams of NaCl over 100 mils of solution, or 100 mils of solution over 5 grams. So again, it's a conversion factor, and this will help us when we're solving problems. So using a conversion factor and solving for the following problem, you need to prepare 225 mils of a 5% sodium chloride solution. How much NaCl will you need? So you're looking for the solute, or the numerator, in the problem. There is 2 ways to solve this. I'm going to first show you using dimensional analysis. So a 5% solution means 5 grams over 100 mils. So if I started with 225 mils of solution, I know that milliliters has to be on the bottom, and my units cancel, so it's 225 times 5 divided by 100 will give me 11 grams. It's actually 11.25 grams, but they round it down. So another way that I could solve this is I know that I want to make a 5% sodium chloride solution, and I know that I want 225 mils and times 100. So this is going back to my original formula. Percent equals either weight times 100, or weight volume times 100, or volume times 100. So remember your math skills, PEMDAS. There's no parentheses, there's no exponents, there's multiplication. So the opposite of multiplication is division. So I'm going to divide both sides by 100. These will cancel. And then what I can do is simply cross multiply and divide. So I have 50 times 225 equals 100x, and I'm going to get the same answer. So it's really whatever you feel more comfortable doing at this point. So now I want you to try it. On a scrap piece of paper, what is the mass of glucose in 435 mils of a 12% weight volume glucose solution? Pick either using the formula or the dimensional analysis way and solve the problem. And then hit play to continue to check your work. So either way, you get the same answer. X equals 52.2 grams. Because in the top one, you're going to have 12 times 435 equals 100x. Two other formulas that we use for concentration are parts per million. So this is the number of micrograms of solute in a 1 milliliter solution, and parts per billion. So on your reference table that I gave you, you will see that there are two formulas, and the first one is for parts per million, grams of solute over grams of solution times a million, and then parts per billion is grams of solute over grams of solution times a billion. So a million is 10 to the 6th, a billion is 10 to the 9th. A solution contains 20 milligrams of iron in a total of 2 liters of solution. What is the concentration in parts per million? Well, you know that ppm is equal to micrograms per milliliter. So we've got to go from milligrams on top to micrograms, and we have to go from liters on the bottom to milliliters. So ppm, as we said, is micrograms per milliliter. So if I have 20 milligrams, I have to move the decimal place 3 points to the right to get to micrograms. And I can do this using my conversion chart in the middle of my table. And to go from liters to milliliters, I'm also going to go 3 places to the right. So I wind up with 20,000 micrograms over 2,000 milliliters, which gives me 10 micrograms per milliliter, or 10 parts per million. In this example, they're showing you that all concentrations can be used as conversion factors. For example, the concentration of cholesterol in a blood plasma sample is 186 milligrams per deciliter. How many milligrams of cholesterol are there in 5 milliliters? So I'm starting with 5 milliliters, and I'm going to change that to deciliters. So we know that in 1 deciliter there's 100 milliliters. Because if I'm at deciliters, I've got to move 2 places to the right to get to milliliters. So one of those equals 100 milliliters. And then you have this conversion factor here, 186 milligrams per deciliter, that can also be used. And then you will be left with milligrams, because that's what it asked for. These are not difficult problems, they just take practice until you get used to lining up the conversion factors. When we talk about solubility, we're talking about the amount of solute per solvent at a given temperature. So there's going to be a limit as to how much solute you can mix with the solvent. So there's three types of solutions. An unsaturated solution has less solute dissolved than what it can actually hold for its given amount of solvent. That means we can add more solute and it will dissolve when added. A solution that has the max amount of solute per given amount of solvent at a specific temperature is considered saturated, meaning it's full. If I add any additional solute, it will simply sink to the bottom of the container. A compound is said to be insoluble if less than 1 gram of the solute will dissolve in 1 liter of water. And lastly, there is a solution that is called supersaturated. A supersaturated solution holds more than what it can hold at a specific temperature. So it exceeds the maximum amount of solute greatly, and then a lot of the solute will precipitate out of solution and sit on the bottom. Generally, the rule of thumb is that the solubility of solids increases with temperature. So for example, if I had a glass of cold tea and a glass of hot tea, I could dissolve more sugar in the hot tea than I could the cold tea. Pressure only has an effect on gases. It will not have an effect on liquids or solids. And generally, as temperature increases, the solubility of a gas will decrease. Why? Because when you increase the temperature of something, the particles tend to move faster, they collide, they spread out. So if you have gas particles that are colliding and spreading out, they're not going to want to go into solution. Another thing to think of is soda. When you open a can of soda or a bottle of soda, you hear that psh sound. That's because when you take the top off, you're decreasing the pressure. When you decrease the pressure, then the gas will come out of solution, and what we hear is the CO2 coming out of solution. And to show you that, you can see here that gases are dissolving better in cooler temperatures. And you can also see that the solubility of a gas increases as you increase pressure, which is shown in the right-hand graph. So solubility also depends on molecular structure. Nonpolar molecules will only dissolve in nonpolar solvents. That's really important. Nonpolar molecules only dissolve in nonpolar solvents. Polar molecules will dissolve in polar solvents as well as ionic. So let's talk about that. Water, for example, if we were to draw water, you know that that is polar. So here's my water molecule. It has 2 lone pairs of electrons on it. This side of the water molecule is slightly negative. This side is slightly positive, making it polar. Oxygen has a higher electronegativity, so it's going to pull the electrons toward it. So if I were bonding to another molecule, even another water molecule, let's say, so let's draw another water molecule over here, you know that opposites attract. So the negative of one molecule is going to be attracted to the positive of another. So right here is our hydrogen bonds, okay? and that allows water molecules to be soluble with one another. Now, you can look at another polar molecule like alcohols. A lot of alcohols have that polar side to it as well. And you know that you can dissolve alcohol in water, because I'm sure some of you are old enough to have had a 7 and 7, or a vodka and tonic. So you're taking ethanol, which is a drinking alcohol, and you're putting it into a substance that contains water. Now, when we talk about non-polar dissolving non-polar, many of you have eaten a greasy steak, or you've had salad dressing that's got olive oil in it, and you know that you can't go over to the sink and just rinse it under the faucet, under water, and the grease comes off. It doesn't happen. The water beads up on it. Why? Because water's polar. Fats are non-polar. Like only dissolves like. So in comes soap. Okay, soap is a very unusual compound because it has a polar end to it, and it has a non-polar end. The non-polar end of the soap is called hydrophobic or water-fearing. Okay, and then the polar end of the soap molecule is hydrophilic, water-loving. So what happens when you have soap? Okay, the polar end of the water molecule bridges with the water molecules coming out of the faucet. The non-polar end of the soap bridges to the fat molecules, and now you have a connection between the two molecules, and it allows you to remove the fat and oil from your dishes. So another example is lauric acid. Lauric acid is a molecule with both a hydrophobic region and a hydrophilic region. You can see that this area in here in yellow, okay, is very symmetrical. That is your non-polar region. It doesn't have any atoms that can form hydrogen bonds. Recall from our bonding unit that hydrogen bonds form when hydrogen bonds with either nitrogen, oxygen, or fluorine. Those are the only time we can form hydrogen bonds. Then we have our hydrophilic end. So here you have hydrogen bonds in here because you have the O and the H. So this side is this oxygen right here is going to have a partial negative. The hydrogen is going to have a partial positive. This oxygen over here is going to be a partial negative. All right? So you've got a polar region there. And just for clarification, we haven't gotten to the unit on organic, but we're starting to talk and look at some organic molecules. Organic molecules contain carbon and hydrogen, often oxygen. So this is a condensed, what we call a condensed formula, where it's written as CH3. And if we were to write it out, it would look like this down below, CH3. So that's the same as this right here. So CH3 matches with this region, CH2 with this region, CH2 with this region, so on and so forth. So the more atoms that you have available that can participate in hydrogen bonds, right, that polar bonding, the higher the solubility in water. The more carbon and hydrogen atoms, however, so that nonpolar region, that very symmetrical area, the lower the solubility. So just rendering molecule size, okay, and comparing a low carbon number chain to a high number carbon chain tells us a lot about how soluble it is. So let's look at this first example here in table 5.3. You have heptane. Heptane is a 7-carbon chain, all surrounded by hydrogen bonds. It is symmetrical in nature, so therefore there is equal charge distribution, which makes it nonpolar. Very, very little solubility. You can see there 0.3 grams per liter in water. Then when we look at heptanoic acid, so now you're taking those 7 carbons that you just had, linked together in heptane, and you're adding a carboxylic acid functional group to the end, that C double bond OOH, which is indicative of an acid. That is the functional group of an acid. Now we have hydrogen bonds. Now we can dissolve in water. And you can see there it has an intermediate solubility in water, 2.4 grams per liter. So what's holding that solubility back are all those carbons on the left-hand side of the molecule, that non-polar area. And then on the bottom one, you have what's called pimelic acid. So this is 6 carbon chain, but it has 2 carboxylic acid functional groups. So it's got 2 acid functional groups, one on the left side of the chain, one on the right side of the chain. Got a lot of polarity on either side of that chain with just a symmetrical region in the middle. So look at how that increased the solubility up to 25 grams per liter by just adding that extra functional group to increase the hydrogen bonding. So let's take a moment to look at table 5.4. These are all acids. They all have that COOH ending, that carboxylic functional group, indicative of organic acids. But notice how your solubility is highest with the smallest carbon chain, as in butanoic in the first structure. When you get down to decanoic acid, which is a 10 carbon chain, look at how low the solubility is, 0.15 grams per liter. Why? Because you have that big non-polar tail hanging out there on the left-hand side, which decreases the solubility of the overall molecule drastically. So let's just apply what we learned about solubility and look at something in our own bodies. So solubility affects how our bodies use and store vitamins. So we have water-soluble vitamins, for example, vitamin C and all of the B vitamins. They dissolve in water, so they are not stored. So as we ingest them, we take them in, whether they be in natural substances or they are in a multivitamin or simply a vitamin C tab, they get dissolved, our body uses what they can use, and we excrete the rest. However, fat-soluble vitamins, as in A, D, E, and K, those are stored in our bodies, and excessive amounts can be dangerous. So if you don't have a diet that's rich in vitamins A, D, E, and K, then you need to take a multivitamin. But certainly if you're getting your recommended daily allowance through your diet, it could be dangerous to be taking supplements of these type if they're not needed. So now that we've discussed most of the important vocabulary involved in solubility, we're going to move to concentration, because solubility is a measure of concentration. So to measure concentration, we use the term molarity. And molarity is the amount of moles per 1 liter of solution. So remember how we talked about a dozen being 12? Well, a mole is also a unit. It's a conversion factor. So last week I had told you that 1 mole equals the gram formula mass, the weight of the substance, whatever it is, whether it be water, H2O. So that's 18 grams. Or it can be Avogadro's number, 6.02 times 10 to the 23rd atoms or molecules. Or 1 mole can also equal 22.4 liters if that substance is a gas. This formula is on your reference sheet. You do not have to memorize it. What you do need to make sure that you're paying attention to is that if you're given milliliters in the problem, you change it to liters. And if you're given grams in a problem, that you get it to moles, because you cannot calculate molarity unless your units are in moles and liters. So let's work through a sample problem. What is the molarity of a solution that was made by adding 3.5 grams of NaOH to water if the final volume of the solution is 0.5 liters? Well, first of all, I know that my formula is moles over liters, and I don't have moles right now, right? Molarity is equal to moles over liters, and there's 2 ways to solve it. I've got my liters, which is right here, but I was given grams, so I have to get my grams to moles. Well, there's another formula, or we can use dimensional analysis, where moles equals given mass over GFM. So I'm going to show you both ways to solve this. Let's start with dimensional analysis because that's really the preferred method and the one that you'll have to use in your medical calculations class. So I'm starting with 3.5 grams of NaOH. I know because on my conversion chart on the very bottom, Professor Nielsen wrote 1 mole equals the gram formula mass. So right here, I need grams. So if I calculate the gram formula mass of NaOH, I've got Na at 23, oxygen at 16, hydrogen at 1. I add all that up, I get 40. So 1 mole equals 40 grams. My grams cancel. That's going to give me moles, okay? And then I can divide my moles by my liters. Or if I don't want to do it that way, I can simply just use the formula on my reference table. I can put my 3.5 grams in here, divide it by 40, right? I'm still going to get 0.088. And then I'm going to have 0.088 over 0.5. All right? So either two small calculations or do the dimensional analysis. So what does it mean when I say you have a 6 molar solution or a 0.5 molar solution or a 1.5 molar solution? It's that many moles in 1 liter. So a 6 molar solution has 6 moles of NaOH in 1 liter of water. So that gives me 2 conversion factors. And we've talked about this, flip-flopping them. So in this next problem, how many moles of NaOH are in 250 milliliters of a 6 molar solution? The best thing that I can tell you is whenever you see molarity in a word problem, the first thing that you want to do is convert it. This is 6 moles equals 1 liter. So if you do that, then you'll know what to do with the problem because you have 250 milliliters and you know that you have this conversion factor that you can use, but it has to be in liters. So if you don't know to move the decimal place 1 point, so here they went to their little conversion chart on the reference tables. They found milliliters and realized you had to move 3 places to the left to get to liters. So we've got 0.25 liters, and then they put 6 moles over 1 liter, so our liters cancel and you get 1.5 moles. If you didn't know that, you could have done 250 milliliters, and there is 1,000 milliliters in 1 liter. So you could have had that extra conversion chart there, and then 1 liter is 6 moles. So now your milliliters cancel and your liters cancel. So 250 times 6 divided by 1,000, you're still going to get the same answer, 1.5. Just another way to set the problem up. All right, so you're going to try this next one. How many grams of NaCl do you need to prepare 35 mils of a 5 molar solution? So you need grams. I want you to pause the video. There's more than one way to do this. I'm going to show you both ways that you can get the answer to, and then you can see if you got it correct, or B, which method of solving works best for you. Okay, so one way that you can do it is in 2 separate formulas. You can see on the top left I have the molarity formula. Molarity equals moles over liters. I knew that I had 5 moles per 1 liter because I would first rewrite this as a conversion factor. 5 moles equals 1 liter, right? So there's my 5 molar right here equals moles X over 0.035 liters. I get 0.175 moles. Then I can use my mole formula. Moles equals given mass over GFM, 0.175 moles, and the gram formula mass of NaCl is, Na is 23, chlorine's 35.3, approximately 35.5. They used the exact here, so they got 58.44, which is 10.2 grams. Now, the way the book showed was going from milliliters to liters, moving that decimal 3 places to the left. Then you know that 5 moles equals 1 liter, get your moles. And then down below they converted the moles to grams, got 10.2, same answer. I prefer to do it all in one shot, which is what you see here at the bottom. You have 35 mils that you started with. I changed that to liters. I then used my conversion factor. 1 liter is 5 moles. Then I used my conversion factor. 1 mole equals the gram formula mass. My units canceled. I multiplied everything on top, 35 times 5 times 58.4, and I divided by 1,000. So, very similar, but slightly different. 3 different ways to get the same answer. One way should resonate with you. Okay, so now we're going to switch gears and we're going to talk about osmosis, dialysis, and tonicity. And to do that, we're going to start by talking about diffusion. So, diffusion is the tendency of particles to distribute evenly in a mixture. And when something diffuses, it goes from an area of higher concentration to an area of lower concentration. So here you can see they put a drop of green food coloring in water at 1 o'clock, and it's very concentrated where that drop is. So what happens is the color tends to bleed out into the water. At 1:30, you can see that it's moving throughout the water, and by 2 o'clock, all of the water is green. So the food coloring moved from an area of higher concentration to an area of lower concentration. That's why if you're sleeping in on a weekend, or maybe when you were younger, you'd wake up to the smell of coffee or bacon in your bedroom. Why? Nobody was cooking in your room. Okay, it's because mom or dad was downstairs in the kitchen, and the smell of bacon and coffee is very concentrated in that area, so it diffuses throughout the entire house, and it makes its way to your bedroom upstairs. So osmosis is very similar to diffusion, except for osmosis refers to the movement of water through a semi-permeable membrane. And it's going to go the same way from an area of higher concentration of water to an area of lower concentration of water. So if I have 2 different concentrations of solutions on either side of a membrane, osmosis will occur. So here you can see in our example, we have pure water on one side and sucrose on the other side. So what happens is that water will go from the pure side to the sucrose side. And after the experiment, you can see that there's more liquid on the right side. Why? Because sucrose wasn't pure. Sucrose contained some water, but less water than the pure side. So as I said, osmosis is the diffusion of water from an area of higher concentration to lower concentration. So it moved to the sucrose side until there was a balance of water molecules on both sides. So this is a slightly different situation. Now, instead of having pure water and sucrose, I have 2 different concentrations of sucrose. Again, okay, think about it. Now, water will move from the lower concentration to the area of higher concentration. So in the end, you will wind up with both solutions having the same concentrations, but notice that the liquid levels are different. And that's because one had a higher concentration to begin with. So how do you know which way the solution will flow? Well, if you have more than one solute, you need to add up the molarities of each solute to determine which direction water will flow. So let's look at this example. you have solution A that contains 0.1 molar glucose, 0.05 molar sucrose. That gives us a total of 0.15 moles. And solution B contains 0.12 moles of glucose. So if they are separated by a semi-permeable membrane, which means that substances can pass through if they're small enough, we want to know which direction the water will flow. So as we said, A has a total molarity of 0.15, B a total molarity of 0.12. So it's going to flow from 0.12 to 0.15. Why? Because it needs to even out the concentrations. So it's going to go from B to A. So A will become more dilute, and eventually they will have both the same concentration. And that concentration would be around 0.135. So we've talked about diffusion, the movement of substances from an area of high concentration to low concentration. Osmosis, the movement of water from an area of high concentration to low concentration. Now we're going to talk about osmotic pressure. Osmotic pressure is the pressure caused by the flow of water during osmosis. So as that water is moving, it's causing pressure. So the greater the difference in concentration between two solutions, the greater the osmotic pressure will be. If one of the solutions happens to be ionic, meaning a metal and non-metal, dissociation affects the osmotic pressure because that compound is going to dissociate into its constituent ions. So for example, sodium chloride would dissociate into Na plus and Cl minus, and that will affect the osmotic pressure. So solution A contains 0.2 molar sucrose. Solution B contains 0.1 mole sodium chloride. If these solutions are separated by a semi-permeable membrane, will osmosis occur? Well, as I just said in my example on the previous slide, the sodium chloride will dissociate into Na plus and Cl minus. So each liter of solution contains 0.1 moles of NaCl, which is the same as 0.1 moles each of Na plus and 0.1 moles of Cl minus. So you're actually forming 2 moles of ions. So solution A has a total concentration of 0.2 because it contains 0.2 moles of sucrose. Solution B also has a molarity of 0.2 because we just said it contained 0.1 moles of Na and 0.1 moles of Cl. So solution A and B are equal in concentration, so no osmosis occurs. So now you try it. If solution A contains 0.05 molar MgNO3 and solution B contains 0.12 molar glucose. If these solutions are separated by a semi-permeable membrane, which direction will the water flow? Well, you need to figure out the molarity in solution A by looking at what the MgNO3 dissociates into. So take a moment and try to figure that out and then check your work. So you should have realized that MgNO3 will dissociate into 3 ions, 1 Mg plus 2 and 2 NO3 minus, because that parenthesis means that there are 2 NO3s. So 3 ions times 0.05 gives me 0.15 molarity, as compared to the 0.12 molarity of the glucose. So my glucose solution is weaker in concentration, therefore the water will flow from B to A. Tonicity is the relationship between the overall concentration of the solution and the normal solute of concentration in blood cells. So you've probably heard these terms used before. Isotonic, solutions that contain equal concentration of that found in blood cells. Hypertonic, solutions containing higher solute concentration than that of blood cells. And hypotonic solutions contain lower solute concentration than that of blood cells. And let's look at this in relation to blood itself and what happens. So if I have a solution that is hypotonic, that means that the solute concentration is less than 0.28 molar, which means that water will flow into the cell. And as water flows into the cell will swell and it can burst or hemolyze. In an isotonic solution, the solute concentration is equal to 0.28, as well as the blood. So no osmosis occurs, there is no net movement in or out of the cell, and the cell is unaffected. In a hypertonic solution, the solute concentration is greater than 0.28, which is going to cause water to flow out of the cell, and the cell will shrink or crenate. Dialysis is the movement of solute particles through a membrane. So remember we talked about diffusion, movement from area of high concentration to low concentration. Then we talked about osmosis, which is specifically the movement of water. So now we're going to talk about dialysis, which is the movement of solute particles. So you know we're talking about a semi-permeable membrane. Well, not everything can pass through the membrane. It depends on the size of the molecule. Only small ones can pass through. So osmosis and dialysis will occur in opposite directions, such that both the water and the solute are moving from low concentration to high concentration. We're going to move from low to high. With this.
Breaking down.
So let's look at this diagram here of a semi-permeable membrane, okay? And you can see on the left side of the membrane, you have a 0.1 molar glucose solution. And on the right side, you have a 0.2 molar glucose solution. So what that means is there's more glucose on the right than on the left, but there's more water on the left than on the right. So water will osmosize from the 0.1 molar to the 0.2 molar. And the glucose will dialysize from the 0.2 molar to the 0.1 molar. Because there is higher glucose on the right than on the left. So remember, that's going to go from high to low. The water is going to go from low to high. Did you tell me I didn't even record that? What is going on? So a new word we're going to talk about now is an equivalent. And that's not a conversion factor. You've heard me talk about different equivalents. Conversion factor is like 1 mole equals the gram formula mass, or a dozen equals 12. Here, an equivalent is the amount of any ion that has the same total charge of 1 mole of hydrogen ions. Well, 1 mole of hydrogen ions are just basically plus 1, because hydrogen only has 1 electron. So if you take it away, it has 1 proton. So the number of equivalents is really equal to the number of moles times the charge. So 1 mole of potassium ions is really 1 equivalent. 1 mole of nitrate ions is 1 equivalent. 1 mole of magnesium ions, the charge is plus 2. So plus 2 times plus 1 is 2. So 2 equivalents of magnesium. 1 mole of S minus 2. S minus 2 times plus 1 is going to be 2. I mean plus 1, sorry. Minus 2 times plus 1 on the hydrogen. So you have 2 moles of S minus 2. So on and so forth. Let's see what we do with this in a problem. So here a solution contains 0.31 moles of phosphate ions. How many equivalents of phosphate ions does the solution contain? So 1 mole of PO4 3 minus, and I got that from table E in my reference tables, is 3 equivalents of potassium ions. So this translates to 2 different conversion factors. 1 mole equals 3 equivalents, and 3 equivalents equals 1 mole. So if you have 0.31 moles, you know that moles has to be on the bottom. So 1 mole equals 3 equivalents, so that's 0.93 equivalents. So in this problem, we're going to have to use multiple conversion factors because you're starting with 25 milli equivalents of a citrate ion, C6H5O7 minus 3. How many grams of citrate ions does the solution contain? So you have to know that 1 milli equivalent, right? So you have milli. So that's 1,000. Milli is 1,000. So 1,000 milli equivalents equals 1 equivalent. So that's one conversion you're going to have to know. And you're also going to have to know, because they want grams, you're going to need the gram formula mass of the citrate ion. So you have to figure that out. 6 times 12 plus 5 times 1 plus 7 times 16. You need that as well. So you can see here, I have 25 milli equivalents. There's my first conversion factor that I spoke to you about. 1 equivalent is 1,000 milli equivalent. 1 mole equals 3 milli equivalents. How do I know that? Because of this 3 right here, okay, that charge. 1 mole equals 3 milli equivalents. And we also know that 1 mole equals 189.10 grams. That is the GFM of the C6H5O7. So your milli equivalents cancel, your equivalents cancel, your moles cancel, and you're left with grams. 25 times 189.10 divided by 3,000. Sometimes concentration is expressed as milli equivalents per liter. For example, a solution contains 25 grams of sulfate ions in a total of 0.1 liters. What is the concentration in milli equivalents per liter? So we're starting with 2.5 grams. The first thing we know is we got to get that bad boy to moles. So 1 mole equals the gram formula mass of sulfate ions. Well, how do I know what sulfate ions are? I can go to table E, and on table E it tells me SO4 minus 2. SO4 minus 2. So I've got 1 sulfur at 32, and then I've got 4 oxygens at 16. So that's where the 96.06 came from. So my grams cancel. We know that 1 mole is 2 milli equivalents. Why? There's my negative 2. That's where that conversion factor is coming from. And we already discussed that 1 equivalent is 1,000 milli equivalents. So I come out with 52.1 milli equivalents. Now I want that in milli equivalents per liter. So how many liters did they give me in my problem? 0.1. So I take my answer divided by 0.1 and I get 521 milli equivalents per liter. These problems are not difficult. It's all about paying attention to the units and making sure units cancel. Here's another example. How many grams of sodium ions So I'm looking for grams of sodium. So that's going to be Na plus grams. That's what I want to find. Are in 250 mils of an intravenous solution that is 130 milliequivalents per liter of sodium ions. So first of all, this can be written, your 130 milliequivalents per liter can be written as two conversion factors, which you see right here, okay? So these equal this, and I can use whatever one I want. I also know that 250 milliliters is equal to 0.25 liters. So I didn't even worry about doing the 1,000 milliliters equals 1 liter. I just used my reference table and I moved 3 places to the left. So I'm starting with my 0.25 liters. I know I'm going to use this conversion factor right here because that's the one that will let me cancel my liters. So now I have 130 milliequivalents. Well, I got to get rid of that milli. We know that 1,000 milliequivalents is 1 equivalent. We talked about that earlier. And I've got a +1 charge here. So I know that 1 mole equals 1 equivalent. And then the last thing I know is sodium. Sodium has a mass of 23. So I probably would have put 1 mole and 23 grams. They use 22.99. Doesn't matter. I just kind of round things to a whole number when they're that close, and I get 0.75 grams of sodium ions. Okay. So let's work through this problem together. How many equivalents of calcium ions are there in 10 mils? I know right away that I can move this 3 places to the left, and I get 0.010 liters, and I have 103 milliequivalents per liter, so that can either be 103 milliequivalents over 1 liter or 1 liter over 103 milliequivalents. We also need to know that 1,000 milliequivalents equals 1 equivalent. So I probably would have started right with my liters because we already changed that, and I would have done 0.010 liters, and then I could have gone right in with this. 1 liter is 103 milliequivalents, and then 1,000 milliequivalents is 1 equivalent. And we would have gotten the same answer, but I just cut out a step because I used my sliding scale to convert my milliliters to liters. All right, the last thing we need to cover in concentration and solutions is dilution. It's the process of adding water to lower the concentration of a substance. So like adding water to orange juice concentrate. Volume and concentration are related by inverse proportion. So if you increase volume, you decrease concentration. And if you increase concentration, you decrease volume. So we can use a formula called C1V1 equals C2V2. The concentration of one substance times the volume of that substance equals the concentration of the final substance times the final volume. And this is also on your reference tables. So you can look at these various examples of copper 2 nitrate, and hopefully you can see that the one on the very left is extremely concentrated and then becomes more dilute as you move from left to right, with possibly zero to little any copper nitrate in the last example. So how you might use this formula is in this example, how many liters of a 6 molar NaOH solution are needed to prepare 1 liter of a 0.15 molar NaOH solution. So first of all, of is always a linking word. So that means that these two pieces of data are going to be linked together on one side of the equation. So this is our final concentration, 0.15, and our final volume, 1 liter. How many liters? We don't know that. That's our V1. That's what we're starting with. Of a 6 molar, that's our C1. So then we simply plug and chug. 6 times X equals 0.15 times 1. So 6X equals 0.15. We divide by 6, and we get our final volume. So if you add 50 mils of water to 25 mils of a 0.9% weight volume solution, what is the concentration of the diluted solution? So you know this is what you're starting with. So this is your V1, and this is your C1, and this is going to be your V2, and you don't know what your C2 is. This is really big. So using our formula, C1V1 equals C2V2, we can simply solve for this. So we've got 0.9 times 25 equals X over 50. And then we solve for X. And I'll show you the answer on the next page. So we get 0.3% weight by volume. Because they gave us the concentration in percent, we can show our answer in percent. So let's go over the highlights of this chapter. Our body fluids contain a wide range of solutes, and good health requires that our bodies be able to maintain many of these at very specific concentrations. As a result, in healthcare, the concentration of a solution can be as important as the chemicals that make it up. Solution concentration is highly important in the health field sciences. For example, knowing and understanding the tonicity of different solutions, either to be administered or already in the body. So the difference between isotonic, hypotonic, and hypertonic. Furthermore, having the knowledge of health conditions, where these solutions are to be given, and the physiology behind such decisions. For example, the goal of giving a patient a hypertonic solution would be to pull fluid from the cell through the process of osmosis. Why? An example of a medical condition requiring a hypertonic solution would be cerebral edema, swelling of the brain. Okay, and that goal would be to pull fluid from the brain cells by causing the cells to shrink and therefore reducing the pressure and removing the water from the brain tissue.